Okay, thanks everybody for coming this unusual day. All right, so we continue our structure theory of Lie algebras, and our next goal is to construct an SL2 triple, right? The same way we did it for SLN, so now we will do it for any simple, semi-simple Lie algebra. So what is our setup? Well, of course, we will always have semi-simple Lie algebra. And we have inside Cartan subalgebra H. Let's take and denote the killing form like that, but it might be any non-degenerate invariant linear form. Okay. So maybe just non-degenerate invariant bilinear form. On G. All right, so if we have this, then there is natural isomorphism, like vector space isomorphism from H. So we have isomorphism from H to H star as follows. You take an element X from here, and the corresponding linear functional is just you computing the form with X. Why is it an isomorphism? Because we said that the form is non-degenerate, right? But I said that this isomorphism from H to H star, right? Not from G to G star, right? So we also have to remember that its restriction of this form to H is also non-degenerate. So remember, if we had like a root decomposition for a toral subalgebra, then its restriction to G alpha tensor G negative alpha gives non-degenerate pairing, right? So here H is G0. So that's why restriction of this form to H is non-degenerate. So we have this isomorphism, and therefore we can actually define the following. So suppose I have also, maybe let me introduce this. No, okay. So so suppose that I have an element alpha in H star. I would like to define its corresponding preimage of this alpha under this isomorphism. Okay? Define H capital alpha from H as follows. As I said, it's just a preimage of alpha under this isomorphism, but we can write it down explicitly. So if I take alpha and compute its value on some element, arbitrary element of H, this will be H alpha with H. This is for every H from the Lie algebra the Lie subalgebra H. All right. Once we do this, we also can define, we can notice that this form induces form on H star. So we had the form on H, now we have also form on H star. So then this induces form on H star. So how do we, if I have two elements alpha and beta that lives in H star, then I compute, so this form that it's induced by this, I will also denote by the same parentheses, okay? It is just by definition this. All right. So let us prove the first proposition of today's lecture. So it goes like this. Right, so let us fix also before maybe, so for today's lecture, since we fixed the Cartan subalgebra, let us also fix corresponding root decomposition. So let G be decomposed as follows: H plus direct sum over alpha in R, G alphas, be the root decomposition corresponding to H, right? So G alpha is a common root, is a common eigenspace for H, right? R is a root system. It's a finite subset of H star, right? And so we just simultaneously diagonalize all elements of H and get such a decomposition, right? Each. So this is just written as decomposition of common eigenspaces. All right. So okay, proposition. Let me take E from G alpha, and let me take F from G negative alpha. Then for some alpha in R. So let for some alpha in R. Then if I compute the commutator, this is something proportional to H alpha. And the coefficient that I have to put here is exactly the form computed on int f. Proof. So we will use the proof. Just use definition of H alpha and invariance of the form, right? So let me take H from H, and then let me compute E and F, the bracket with H, like that, right? So using invariance of the form, I can write this down as follows. It is right. Well, E and then F H, right? Then F, adjoint action of F on H, or rather I should take minus, right? So I would like to say that this is E, and this thing is alpha of H times H. Times what? Times F. Right? Just because F is from G negative alpha, what does it mean? Right? It means that if I take adjoint action of H on F, it will be it will be negative alpha of H times F, right? So hence, I have a commutator here in the wrong order, so I have minus two minuses, and so no minuses as the result. Right, so this is alpha of H. Yes? Mm-hmm. So I have this, right? And this is just number. I factor it out. Now what I have is that for every element in H, right, this thing, right, E H, right? So this as a linear functional, right, is the same as linear functional like that. Alpha computed on something that I put inside here, right, times this number. Sorry, EF, right? So just by definition means that this thing is so EF is EF H alpha. By definition, of H alpha. Right? Okay, very well. So we proved this proposition. Okay, so to create SL2 triple, we will need, so H alpha will be H, right, in this SL3 triple. But with some coefficient, to create this coefficient, we would like to divide by the norm, by the alpha, the form of alpha and alpha with itself. So we would like to prove that it is actually not zero. Okay, so this is our next lemma. That for every alpha in R, the form of alpha on itself is not zero. Proof. So proof will be by contradiction. All right. So let me take some alpha from R, and let me take E and F. So E, again, from G alpha, as just standard, right, procedure for us already. F from G negative alpha. And so let me take, so consider this such that I also would like the form of them to be non-zero. I have right to do so because the form is non-degenerate on restricted to G alpha tensor G negative alpha, right? Okay, very well. So let me also take commutator of these two things, and I would like to call it H. All right. So now suppose that alpha with alpha is 0. Then I compute what? I compute E with H, so H with E, the bracket. Right, this will be the following. Right. Just because E is from G alpha, right? This is alpha of H small times E. Right. So I'm claiming that this is actually 0. Why? Because, well, we know that E with F is this, right? By proposition that we proved before. Therefore, let me just plug it in here and see what happens. I have alpha of this, right? So I have alpha of H of alpha, right? And then this is some number that I can, factor outside. So let me write this down: EF, and then E. Okay, this guy is alpha with itself, the form of alpha with itself, just by definition of H alpha. Therefore, it's 0. So therefore, the whole thing is 0. So H commutes with E, if I have this assumption. All right.
Where is this supposed that which letters
Here?
Another one. Equals to the previous one.
Yes, here.
Yeah.
So this is alpha with itself. Sorry. Yes. Mm-hmm. So analogously to that, we can prove that H commutes with F. So similarly, H commutes with F. Okay. So therefore, what we get? So let us take the algebra spanned by E, F, and H. So, but then span of E, F, and H. It is something familiar, right? How is it called? What's that? No, not yet. So because I assumed something bad, it's not SL2. It is Heisenberg, three-dimensional, right? So H with E commutes, H with F commutes, and E with F gives me H. Right? Replace E, F, and H with, more familiar X, Y, and Z. This will be Heisenberg. So I am assuming something bad. That's why it happened to be noticeable too. Right?
Just a one-dimensional.
No, this one is three-dimensional with one-dimensional center. Commutant, sorry.
Even with this commutation relation being zero, it's one-dimensional. It's three-dimensional.
Yes, yes. Still, you have three bases consisting of three elements, right? They are all not zero, and they're linearly independent, so three-dimensional. Anyways, but the main point is that it is solvable. Okay, and that we know like from lecture 1. So, is solvable. So then by Lie theorem, we can choose a basis in G. Yes, can choose basis in G such that at F, at E, and at H are upper triangular. Right? But moreover, if I take at H, then it is a commutator of at F and at E. Right? So if I take two upper triangular matrices, commute them, I will get strictly upper triangular. E is strictly upper triangular. But this means that H is nilpotent, right? But H is also in the same time as semi-simple because it's an element of total subalgebra, right? So it's what is the only element which is both semi-simple and nilpotent? 0. Right. But this is, of course, the contradiction. Right, so H is also semi-simple. Therefore, H equals 0. But let's recall what was H at the very beginning. It was this thing. This is non-zero vector. This is non-zero. We chose it to be non-zero, right? But this is E, F, H alpha. So this is contradiction. Therefore, what we assumed is a bad thing. This doesn't happen. So.
Can you remind me of why H alpha is not zero?
Well, H alpha is not zero because the form gives isomorphism of vector spaces. You take a root, it's not zero by definition, and of course its image under this isomorphism is not zero. Very well. So we proved lemma, and now we can divide by alpha and define the following element H small. So denote h alpha small to be 2h capital alpha divided by the norm. Let's call it the norm, although we don't have inner product yet. Okay. Then we have now SL2 triples. Why? Because of the following proposition. Okay, so suppose, or maybe, okay, suppose that E from G alpha, F from G negative alpha are such that I need something again for their for the form of E and F. Okay, I think it should be like that. So this I can do because this is some non-zero number. And again, the pairing is non-degenerate on G alpha tends to G negative alpha. Right. Then, for such E, F, and H alpha small like this, we have commutation relations like in SL2. So then E with F is H alpha. What? H alpha with E is 2E, and H alpha with F is negative 2F. Okay, let's check. Maybe, well, the check is easy, so let's do this. The first one, so proof. It's kind of clear, right? So you have E and F, which we prove that it is the form of E of F times H alpha, right? This we agreed to take alpha 2, right, over alpha alpha, right? And then H alpha is this. If I express H alpha capital through H alpha small, is this one, right? Okay, this cancels and I get H alpha. Oh, so let's check, say, with E, and then with F it's just similar. So H with H alpha with E. Let's see. So this is alpha of H small alpha, right, times E, just because E is from G alpha. Okay, here I need to insert this expression of this in terms of H capital alpha. So this will be alpha of H capital alpha, right? Maybe the constant that I have there, I would like to write outside. And the constant is 2 over the norm and times E, right? So let me maybe write E here. Okay, alpha of H capital alpha is actually the norm, right? Alpha with alpha. right? So this is alpha, alpha. Or maybe let me not. So this cancels with this, right? And so we have 2e. So we're done. And this is similarly, if I have f here, I will get minus here. I will get minus at the end. Very well. So you see now we have a bunch of subalgebras which are isomorphic to SL2, which are deserved to be called SL2 triples. Rather these elements, right? So these elements, right? So we proved. And next, let's give a couple of definitions and notation. So elements E and F and H alpha, where E and F, like in the previous proposition, are called SL2 triple. And also, I would like to give some notation to this subalgebra for some concrete choice of alpha, right? We will need this. So we also would like to write the following. So I would like to write SL2 with subscript alpha. So by this, I will mean the subalgebra which is spanned by this E, F, and H alpha. Okay. Very well. So now this is a good instrument for us to proceed, because we know a representation theory of SL2 very well. And then we would like to apply this to adjoint, to actually adjoint representation, actually to representation of SL2, which is G, right? And then this will give us a lot of things. In particular, we have the following. So let's call it maybe theorem. I don't know. It has four parts. First of all, so maybe here, V alpha, which is the following vector subspace of G. It is CH alpha plus direct sum of GK alpha as K runs over all integers, but without 0. Well, if K is 0, then we have already this term here. So if we denote such subspace V alpha, then I claim that it is irreducible representation. It is an irreducible representation of SL2 alpha. Second is the following. For any alpha for any root alpha, we have that corresponding root subspaces are one-dimensional. Number 3 is that, okay, we have this irreducible representation of SL2 alpha, but we have a bunch of others, right? You can think of SL3, all these pictures of SL3. You in different directions, you have like maybe we can say like a fibration of this SL2 representations, all right? So we have a bunch of them, and if I denote by V alpha beta, this direct sum, G beta plus K alpha, as K runs over integers, right? Here, alpha and beta are some roots, is an irreducible representation of SL2 alpha. Maybe here I also should add that alpha I take to be a root. Okay, and I promised you 4 parts in this theorem, so the 4th one is the following. The 4th one says that G, so if I take alpha and beta roots, but also I claim I would like alpha plus beta to be root. Then G alpha bracket with G beta is G alpha plus beta. So before we had inclusion, remember? But now if all 3 these things are roots, we have equality. Okay, so let's prove that. Okay, so let's prove this in the order that we listed. All right, so it's easy to see that V alpha is invariant subspace with respect to the action of SL2 alpha. Maybe we can check. Okay, so let's check that V alpha is invariant subspace. So I just need to take E, F, and H alpha, SL2 triple, and act on elements from here. I would like to obtain elements in here again, right? It's kind of clear that if I would like to use like linearity of a joint action and just take some element from living in direct summand, right? So if I take something from here, right, H alpha. Right, so it's a bunch of checks. Maybe we will not do all of them. So one important is the following. I take H alpha, it's an element of SL2 triple, and act on something from G K alpha. Right, so this is from, well, this is easy, maybe, okay. Right, so from GK alpha, no, this one is easy. So, well, let's finish it anyways. So this belongs to G, K alpha. So I act means I take a commutator, right? So this is just K alpha of H alpha and then X. So obviously it's still in there, right? It just doesn't move. What if I take E and apply to the same X? Right? So if I take E and apply to the same X, right, I would like to see, so X lives in GK alpha, I would like to see that this lives in GK plus 1 alpha. So that's my goal. All right. So what does it mean? So let me now, so it means that I would like to take H alpha and act on this element, right? And the corresponding eigenvalue will be given by this subscript. Okay, so if I act by H alpha, right, I will need to compute this, right? But maybe let me not, use brackets, because I will have like a lot of commutators, right? So I will just take E, write E next to X, and it means that it acts, right? So I have H alpha E X. This is just my notation. I don't have bracket here. So now let me move this through. I will have E H alpha X plus commutator of H alpha E applied to X, right? Very well. So okay, let's see what happens. If I have this H alpha, I know how it acts on X, right? Right, it just gives me actually, I don't even need alpha here, right? I would like to take any element from H, right? To check this. Okay, so let me not take alpha in here. Just here, I just take H from the Lie algebra H. Then what happens? So when I apply H to X, right, I will have E, and then I will have alpha of H, and then X. So this is this term, plus the commutator we know, right? So plus, because E is from G alpha, right? So sorry, X is from K alpha, from GK alpha, right? So therefore I should write here K, right? But E instead is from alpha, just alpha without any K. And here was written H acting on E, right? So this I can write alpha, right, of H E applied to X. In any case, what I have is K plus 1 alpha of h ex. Right, so therefore element ex, right, which is this one, just e acting on x, right, belongs to gk plus 1 alpha. Okay, so in the similar terms, you act by f, you get k minus 1 here, just similar check. So therefore, it's invariant, right? If I act by h, I acted on these terms, right? Well, you have to check this separately, but it's also of the same kind of check, right? Okay, very well. So we have that. So other checks are similar. So we have that it is invariant. We would like to see that it is irreducible. How to see that? We would like to look at weight subspaces of this representation. Right? Do you remember what is a weight subspace of a representation of SL2? Yeah, but it's okay. Weight subspace is a is eigenspace of something, right? First of all, of what? Yeah, what element of SL2 triple? H, right? H, eigenvalues of H, they are weights, right? So therefore, I would like to act by H on different parts of this and see what weights I have here. Okay, so that's another plan. So let me take H. H alpha in this case, right? So if I take H alpha and act on H alpha, I'll get 0, right? The commutator of H alpha with itself is just 0, right? So therefore, H alpha, CH alpha, right, is inside the 0th weight subspace of V alpha, right? So here we denote by V alpha mu weight subspace of V alpha of weight mu. Very well. But now let me take H alpha and act on some other direct summand here. So let me take X, which lives in GK alpha. I compute commutator. We already had it here, right? This is K alpha, right? K alpha. And of what? Of H alpha. Times X, right? Therefore, this is the weight. So therefore, I have the following. Maybe let me not erase the theorem and go back and forth between these two. This is also theorem. Okay. So we check that it is invariant. Now we're looking at weight subspaces. Right. So, anyways, I have this. By the way, what is this number? We can see right away. Right, just remember definition of H alpha. So alpha of H alpha. Maybe somebody has any idea. I think we computed it also when we checked the commutation relations for the triple. Okay, so let's check. So we need to plug in H capital alpha, right? But we get then 2 over this. Right, so this is alpha alpha 2 over alpha alpha, right? So this is the 2 that appears in SL2, right, when we compute commutation relations. So actually, what I have here is 2kx, right? Therefore, we checked that gk alpha is inside V alpha with the weight 2k. But remember that if we have a representation, in our case V alpha, then it is decomposed as the direct sum of weight subspaces, right? So you actually have V alpha is direct sum of V k V alpha k as sk runs over z, right? Now, so we have gk alpha is inside here, and ch alpha is inside here. So suppose at least one of these inclusions is proper. But then this decomposition, by these two decompositions, it means that V alpha is a proper subset of itself, right? So it cannot happen, right? So therefore, we have that gk alpha is exactly the weight subspace of V alpha of weight 2k. Now, we have two important observations to make. One is that all weights in our presentations are of the same parity. So, weights of V alpha are of the same parity. And the second observation is this parity is even, right? And the second observation is that weight subspace of weight 0 is one-dimensional. V alpha of 0, so dimension of this is the same as dimension of C as the span of just single element H alpha. And this is just 1, of course. Now recall how representations of SL2, how they look like. So let me remind you. So if I have some representation, then first of all, it's a direct sum of reducible representations, right? A finite dimensional representation of SL2 is a direct sum of reducible, and each reducible looks like this. It has some highest weight, lambda, and then I go by step 2 until I reach a negative lambda. Right, so each in our case it's V alpha, right? It's such picture plus direct sum of some other picture, right? You just maybe start with some mu and do the same thing. And so on. But we say that all these lambdas and mu's, they are of the same parity. That's our first observation there. And on the other hand, this parity is even. Therefore, we have 0 in each of these summand, right? Since we have 0 in each of this summand, dimension of V alpha of 0 consists of number of points that I have here, right? So therefore, we have only one summand, and the representation is irreducible. Okay, is that clear? Right. So I have. So suppose I don't know. I need to have maybe one more here, right? Then this is 0. And how many points I have in this 0 line, right, is actually dimension of V alpha of 0, which we say that it's 1, right? Therefore, we just have one line, and V alpha is irreducible. Okay, so we proved first one. From the first one, we immediately have second one. Why? Because G alpha is, according to our computation right here, the weight is exactly weight subspace of weight 2 of V alpha, right? So G alpha is V alpha of 2. But since we already proved that V alpha is reducible, then all weight subspaces are of dimension 1, right? So therefore, dimension of G alpha is 1. So we proved the first two. Now the third one. The third one is actually the same sort of reasoning. Now it's just the weight subspaces. Maybe we can compute the little bit different weights, right? Right. So this is the proof of second one. The proof of third one. So now we have some other vector space. All right. I will not again check that it's invariant. So again, similar check, right? V alpha beta is invariant. So this is similar check to V alpha. we just need, again, to look at weight subspaces, right? So let me take, again, x from this summand here, g beta plus k alpha. And act by h. Act by h alpha, actually, right, on x. Then what do I get? I get beta plus k alpha, right, of h alpha, right? So these are all elements of h star. I apply it to this times x, right? Okay, very well. So this is, by linearity, this is beta of h alpha plus k alpha of h alpha we computed is 2, so plus 2k. So this is the weight, x. We actually can compute this a little bit more explicitly. So this is beta 2 beta alpha over alpha alpha. If you remember what is h alpha, how it's again computed through h capital alpha plus 2k x. So this number is pretty important. We will see this over and over again. This is, I don't know, this is an entry of what's called Cartan matrix. So, right, this will be a very familiar formula for us. Anyways, for now, let us just fix alpha and beta and call this thing to be some weight mu, right? And then, okay. And then what we computed is that g, so maybe again, let me go to this board. I have that g beta plus k alpha is inside v alpha beta mu plus 2k. Yes, like this. Is subset of it, right? But again, since we have weight decomposition of v alpha beta, right? Suppose at least one of these inclusions is proper, it's not equality, then from this decomposition and this decomposition, again, they contradict each other. Then. So therefore, v alpha beta of mu plus 2k is exactly g beta plus k alpha. Okay, so therefore again, the parity of weight subspaces is the same. We cannot say it's even or odd now, but it's the same. What's important, and the dimension of all weight subspace is 1. This we proved already. But this again means that it's we just take the same picture that I just erased and take just a random line in there. It still should be 1, right? So dimension of V alpha beta mu plus 2k is 1 by part two, and parity of weights of V alpha beta is the same. So therefore, V of alpha beta is irreducible. And now, what's left to prove this is number 4. So we know inclusion, right? We know that dimension of this is not bigger than. So dimension of this. So since it's a root, it's not 0. So dimension of this is exactly 1, right? So therefore, we would like to prove that this thing is not 0, right? We would like to prove, so for 4, it's enough to check that G alpha with G beta is not 0. It's since it's inside here, it's either 0 or the whole thing, because this one is one-dimensional, right? So how to do that? Right, again, we will use number 3, right? And so G alpha beta, G alpha plus beta. Again, look here. We just need to take k equals 1, right? So therefore, it's V alpha beta of mu plus 2. So so since alpha plus beta is a root, this thing is not 0. This is because alpha plus beta is a root. Now, therefore, this thing, this weight subspace is not 0. Therefore, mu is not the highest weight in this representation. Mu is not the highest weight. Right, so if I take G beta, again, G beta is exactly V alpha beta of mu, right? So since mu is not the highest weight, it means that if I take something non-zero from here, act by E, I will get something non-zero in here. If I act by here, get something, it gets 0, it means that mu is actually highest, right? But I know that it's not highest. Sure enough, I can get by action of E to here, right? So therefore, E with x where x is in G beta and E is from G alpha, right? So this is my E from the SL2 alpha, therefore it lives in G alpha, right? It should go to G to here and to be non-zero. But that's exactly what I would like to prove, right? That I would like to find some element in this which is non-zero. So I proved it. Okay, so the theorem is proved. But that's not that's by no means not all the things that we can get by applying now the instrument of SL2 triple and representation theory of SL2. So another bunch of statements is just saying that R is an abstract root system. Okay, so now we need to define what it is, abstract root system. Not related maybe to any semi-simple algebra. So abstract root system is actually something very that you can, in a sense, touch. So because you can draw it, so it is on a Euclidean space. So you start with an Euclidean space. So let E be an Euclidean space. What does it mean that I have Euclidean space?
You have a non-degenerate inner product on a real space.
But inner product by definition is non-degenerate, right? What also I need a positive definite. Symmetric positive definite, yes. And usually when I say Euclidean space, it's finite dimension, of course, right? Right, so therefore, I also fix inner product, right? When I say Euclidean, I fix inner product. So it means it's positive definite. But when I say positive, it means that I restrict myself to reals, right? First of all. So E is, of course, real finite dimensional vector space. Right? So in particular, E is a finite dimensional real vector space. Okay, and abstract root system is a subset of E. So a finite subset. So by definition, a finite subset of E subset, let's call it R, is called an abstract root system if the following things happen. So you have, first of all, I would like R to span E. Second, I would like, so for any pair of roots, this number that we already saw, 2 alpha beta divided by beta beta, is an integer. and 3 for any pair of roots alpha and beta in R, if you take beta and reflect it with respect to alpha. So what does it mean? Just explicit formula. You take beta and subtract its twice its projection to alpha. So alpha beta to alpha alpha alpha. So if this, so for any, this is also a root. So if these three things happen, then R is called root system. So if additionally I have fourth thing, so by tradition I write something fourth on this board, right? So if additionally we have the following condition, let's call it number 4. So if alpha and beta are roots and alpha is C beta, then C is plus or minus 1. Then, so if additionally we have this condition, then R is called reduced root system. Okay, so now having this definition, we formulate another theorem. So first of all, we would like to have Euclidean space. Before that, all spaces we had were by default complex vector spaces, right? So let me take H star R. So let this denote the span, and by the way, linear span of my root system. So I have take all the roots and consider linear span of my roots. This will be some real vector space inside H star. Okay. Then what? Then this form that we introduced on H star restricted to H star R is real and positive definite. Thus making HR star to be an Euclidean space. And moreover, so this is part 1, and part 2 is that Okay, so this is, again, if before R was just abstract root system, this R is some root system that we fixed in the beginning of the lecture, is corresponding to semi-simple Lie algebra and Cartan subalgebra H. Okay, so then the second, this R, right? Right. So this is root system of semi-simple G is a reduced abstract root system on H R star. Okay, so maybe let us prove at least the first one. Okay, let's try. First of all, notice, so proof and on the way of proving the first one, we already proved that this is integer for R. So we had this G beta, right, is V alpha beta of mu, right? Where mu is actually n alpha beta. That's what we had 2 alpha beta. Only the other way around was beta alpha, right? In our notation, like this. So, n beta alpha is a weight in a weight subspace of a reducible representation of SL2, right? And this is not 0, right? Because beta is a root. This is not 0. Therefore, mu or n beta alpha is indeed a weight in a representation of SL2. Therefore, it's integer, right? So therefore, n beta alpha is integer. So let us use that. Okay, so if my alpha and beta are 2 roots, let me compute this. So the killing form of H alpha and H beta. Killing form of H alpha and H beta is what? So let's recall it's trace of at H alpha at H beta. These two things are diagonalizable simultaneously, and I also know how to write their the eigenvalues. So I have root decomposition, right? So I have the eigenspace decomposition for simultaneously for all elements like this, right? So I claim that this is exactly the following thing. So this is sum over roots of gamma of H alpha, gamma of H beta. Right, so what are eigenvalues of this thing? These are exactly gamma of H alpha as gamma runs over roots. Right? So this is a diagonal matrix in the corresponding basis with entries, one root of H alpha, another root of H alpha, and so on. This is also diagonal matrix of the same form. I multiply them and sum over this diagonal. So that's what I get. Right? But then this is exactly my n gamma alpha. If you recall what H alpha was H capital alpha divided by alpha alpha. Gamma of H capital alpha is gamma with alpha, right? So it's 2 gamma with alpha divided by alpha alpha. So it's exactly my number that I have here. And this is n gamma beta. What I need for now is that they're integers, but what I need is they're real, right? So therefore it's in R. K of, if I take the same alpha equal to beta in this formula, then what I will get? I will get sum over gamma of H alpha squared, right? And each of this thing that I square is real, so therefore it's positive. So the overall thing is positive. So it's greater than 0. But we also have that, let's plug into this the definition of H small in terms of H capital. I will have K of H capital alpha. K, sorry, is killing form, so just maybe I don't need to use this letter. So killing form is just by our notation is this, right? So H alpha, and then I have also some number that I have to factor out, and the resulting it's so 2 divided by alpha. So 2 divided by and I need to square it, so like this. By definition, this is also alpha, right? So it's 4 alpha divided by alpha squared. This cancels, so it's 4 divided by alpha, right? So therefore, so this guy is greater than 0. Therefore, alpha is greater than 0. It's real and greater than 0. And what's left to prove is that alpha beta, this, is real. Then I'm done. So this is by definition, again, H capital alpha with H capital beta, killing form of this. But this is the following. It's the form of H smalls with some coefficient, and this coefficient is this. Times So alpha alpha divided by 2 times beta beta divided by 2. This is again the relation between small and capital H's. So like this, right? And therefore, so this is real, of course. It's positive. This is real. This is real. So therefore, we all think it's real, right? So we're done. So this is real. This is positive. So we proved. So the first part is proved. We still need to, and something is also is proved like this is also needed to see that R is an abstract root system. So we need to prove that reflection gives me again the root, and we need to check that it's reduced. So this we will do next time.